Hey, what's up, YouTube? So I am looking at my optimal start blocks in the field here. We'll get into this next week. This is the quadratic model running inside the Java code in here, but I am getting some good performance out of these program objects which you can download from the vibecoder repo. But there's some metrics that we're calculating, which we'll get into a little bit later. But so I'm actually calculating that on this block with only a couple days of data, running the quadratic model, which we haven't got into yet. But we predicted 10 minutes of warm up, which was for a VRF zone, and we recorded that it actually took 11 minutes and 11.14 minutes of warm-up time, and then our error is about 30 seconds. So for a VRF system, a cassette where this optimal start block is running, I am getting some good performance that I can see with only a couple days of data on the quadratic model. So yeah, feel free to reach out if you want to try installing these. I'm having better luck with the built-in Tritium Optimal Start, which hopefully Tritium will update. Also on these blocks, you can drill into the AX property sheet view. You can see all these parameters, and there's some hidden slots that we link in the schedule next time. And also here's our linear calculations, even though we're using a quadratic model to actually start the equipment. We do actually just kind of calculate a linear degree per heat and cool, which we've been talking about. It's mostly just for us, the humans, so we can see what it's doing. We currently have 4 days worth of data, and this will automatically retain only 15 days of data. So like the oldest days will get shuffled out, and we'll keep on continuously catching newer performance records for both heating and cooling. And you can just see, there's just some interesting parameters, kind of similar to what Tritium has. And it's working pretty good on VRF cassettes and heat pumps. And I'm also trying these on variable volume air handling unit systems too, where one optimal start block will start the air handling unit based on a zone average of the VAV system. So try it out. I highly recommend it. Okay, so let's get out of this. I am gonna dial into the website here. So if we go to our repository for the math, we're still in this model 0, just the easier linear stuff. Still talking about this, the linear model, a little bit more Python code today. And we're actually on day 5, which is actually, I think I pretty much covered it on day 4, but tuning the alpha parameter. So, we walked through this yesterday, actually, same code base, so this video won't be very long, but tuning this alpha parameter, which will basically have like a different effect on the degree per minute that you can, that will model the minutes output. So if I go in here, day 5, all right, so smoothing factor, alpha controls how much weight you give the latest observation and relative to the historic average. So a small alpha parameter of 0.1 means estimated changes slowly, while large has a drastic effect. So like the linear model on the optimal start block that from the vibecoder repo has a 0.5 value. Choosing alpha is a trade-off between responsiveness and stability. Too small, the model adapts too slowly. The seasonal changes, too large, and estimates, becomes noisy. Just for the estimated for the EMA, the exponential moving average. Apply these concepts using the formula, refer to the many examples of understanding. Concept allows you to build more accurate and efficient optimal start models. So this is like what we, pretty much the same thing we did yesterday. So here's our exponential moving average equation in our different alpha parameters. So the lesson today is how much of an effect do these different alpha parameters have? And these were the same thing that happens in the Java code. We're just using Python here because it's a little easier to look at. This would be the oldest degree per minute warm-up, the second oldest, third, these are actually newer values, sorry. So as we like slide through these window of time, these different alpha parameters will have a different effect on the exponential moving average. All right, so should we try this out here? So one thing worth mentioning is, like we talked about this a lot already, is the Tritium optimal start block only uses yesterday's data, retunes it, uses yesterday's data, retunes it, so it's only one day of data. So what we're trying to do in this model 0 is just get a little bit better performance. We can hold 15 days worth of data by default, and then we plow through it on this exponential moving average and kind of get slightly different, better results rather than only one day. And then these alpha parameters, we can kind of tune it basically. So we talked about this yesterday. So we could have one random outlier, could be occupancy, it could be weather, causing the degree per minute calculation to just have a little different effect. So this these alpha parameters will kind of smooth out that data. So let's say these were kind of cold days, and then there was a warm day where we only have 0.18 degrees per minute warm up, and then we got cold again. If there's big fluctuations in occupancy, weather patterns, this will have different effects. Okay, so we could so let's so the tutorial wants us to run this code base. So I am just going to copy it in and just do Python run our script. All right, so this is what we'd be coming up with now. So with an alpha parameter of 0.1, we come up with 0.2 degrees per minute. With an alpha parameter of 0.5, we come up with not much difference. With an alpha parameter of 0.9, we come up with 0.19 degrees per minute, which will have a little bit of a different effect on when we calculate minutes. All right, so this wants to, using the code above, try adding an extreme observation into the mix, and how do the EMAs changed? So maybe I'll just do, all right, so maybe I'll just throw this in here. So not too much actually. So like, it's kind of interesting, I guess, because we can still see the old values. So when the alpha parameter was real small, we have a bigger difference. And when the alpha parameter is bigger, there's not much difference at all compared to 0.193 and 0.194. So bigger the alpha, the more smoothing, I guess. Like you don't really notice much of a difference, but when the alpha is real small, if you have wild fluctuations, we could even put a really small wild fluctuation. So let's say we do 0.02. See what this has, and add in another wild extreme fluctuation. So we get the exact same numbers. maybe even delete out this other one just to see what the calculations look like. So yes, it looks like yeah, I think you get the point though, that alpha makes a big difference, especially when there's some like wild fluctuations in the data. Put in a really small number. Kind of fun to play around with. So I think this would come in handy. Let's say you're running the linear model in a program object, or whatever kind of optimal start algorithm coding language you're using, and you're kind of getting some poor results, like you're overshooting or undershooting the actual minute calculations through the warm-up time. You could actually tune your alpha potentially to just be more accurate. So like when, for example, like when the equipment is supposed to start 7 o'clock and we're calculating we need 20 minutes of warm-up time, and it's actually requiring 30 minutes of warm-up time, or it's too much or not enough, like this alpha parameters, you can tune those. So that is what I'm getting out of this. Okay, so we kind of talked about that. Create a simple Python file that performs a calculation from this left using only basic variables with the quick print. So we did that. I'm just not going to do that because it gave us the Python code to use here. So I think what would be kind of fun though is to just maybe add to this. Let's say print EMA final, which could be EMA. So that is our final EMA if that was our tuned observation. And then if we kind of thinking back on the last tutorials, let's say our occupied zone set point, our occ zone set point is 72 degrees Fahrenheit. Use metric if you're used to looking at metric units. I just use Fahrenheit because my brain is so used to looking at that. Let's say our zone temp at the time is, let's say it's 66. So then our delta temp would equal occ zone set point minus the zone temp. Oops. So if we print our delta temp just for some validation, so we have a 6-degree delta temp. And then if we wanted to back calculate minutes, which is the most important thing in my opinion in these optimal start algorithms, is how many minutes do we need to condition the zone. What did we do yesterday or the couple days before? Like we did, I think it was dividing delta temp divided by EMA. Let's see, so we'd say minutes equals, okay, so these were in degrees per minute, and if we want to calculate minutes, we just need the units to cancel out. The inverse or whatever. 31 minutes. So this data is degrees per minute, and we just need to cancel out our units to get minutes, and then our optimal start equation would be looking that we need approximately 31 minutes to condition the zone. So that's our modeled minutes based on that observation data and whatever our last EMA was, pretending that we found a good one. And we could even, just for fun, come on. We could even just go like that and just see what our minutes calculation looks like here. So if I just delete some of these print statements, so I'm going to delete this other print statement, comment it out. So EMA final here is 0.18. Here it was 0.19, and our minute calculation is slightly different. Not too much, I guess, but maybe it doesn't have that much of an effect. But it is kind of like similar data to like what I experience in the field, maybe, I guess, that we could have a couple days like this, even into some 114 minutes. So you can see how these calculations can fluctuate wildly. So it's important that we're actually watching this stuff and we have a good alpha. That is all for this video. I think let's look at the day 6. I think there's one. So day 6 is probably pretty similar. We're just still looking at these exponential moving average linear models. Day 7, I think, would be the last day for the linear model. Week 1 in review, limits of linear. So in theory, I think these linear models don't perform very well. So we have just like 2 more days of the linear models. And then we get into the quadratic regression. Alrighty, see you guys for day 6.